Welcome to the Deep Dive. We're your shortcut to getting up to speed on complex topics. We dig into the sources, pull out the key insights, and serve them up with, hopefully some surprising facts and maybe a bit of intellectual humor.
That's the plan.
And today, we're diving into a really interesting corner of the online encyclopedia of integer sequences. This is especially for you number theory students listening in. Our mission today is a deep dive into OEIS sequence A000270. It used to be known as discordant permutations.
Right. And our goal is to really unpack what makes A000057 tick. Not just the definition, but, why it's interesting, how it connects elsewhere in math, and some of the historical quirks around it.
Discordant permutations. I like that name. It sounds intriguing, doesn't it? Hints at some complexity.
It does.
So we're going to explore what makes them unique, their definition, some interesting properties, and maybe uncover a little mathematical detective work. Let's get started. Okay, so let's start with that name, discordant permutations. It comes from the 1973 Handbook of Integer Sequences by Sloan. But what does that actually mean? What is a discordant permutation here?
Well, okay, the formal definition, and this is thanks to William P. Orrick's clarification in 2020, is that for n greater than or equal to 2, an counts the permutations of the numbers 1 up to n plus 1 that are discordant with two specific reference permutations. One is just the identity, 1, 2, 3.
Yeah, everything in its place.
Exactly. And the other one is a specific type. It has one element fixed, a one cycle, and the other n elements form one big cycle, an n cycle.
Whoa, okay. That's quite specific. Can you break down discordant a bit more and maybe refresh us on one cycle and n cycle?
Sure thing. So discordant basically means they don't match up. If you compare your permutation to one of the reference ones, discordant means no element is in the same position.
Like a derangement, sort of?
Yeah.
But against two things.
Kind of, yeah. It's about avoiding fixed points relative to those two specific structures simultaneously. Now, the cycles. A one cycle is just an element mapping to itself. Like 1 stays as 1.
Got it.
And an n cycle means the other n elements all swap around in one continuous loop, like 2 goes to 3, 3 goes to 4, and the last one goes back to 2. One big circle.
Okay. So we're looking for arrangements that avoid matching both the everything stays put pattern and this one thing stays put, the rest cycle pattern.
Precisely. That's the core idea.
And that specificity leads to some fascinating math. You mentioned a formula, a recurrence relation.
Yes, a key one is an bn plus 1 plus bn1 for NAs 2.
And the BI there. Those are the Menage numbers. OEIS A000179.
That's them. The famous Menage number.
Okay, I remember those. That's the problem about seating couples around a table so no one sits next to their partner, right?
Exactly, that classic problem. They count as sort of a constrained derangement on a circle.
So, how on earth do dinner party seating arrangements connect to permutations being discordant with these two specific patterns? Is there some, hidden structural link?
That's a great question. And yes, that's what's so fascinating here. The fact that this sequence, AN, defined by discordance with two permutations, can be built from Menage numbers.
Yeah.
It suggests a deep underlying combinatorial structure that connects these seemingly very different problems. It shows how abstract patterns repeat across mathematics. It's really quite elegant.
It really is. So what are the first few terms? You mentioned the formula starts at N2.
Right. The sequence starts at 01, A11, then A20.
Right. Okay.
Yeah, A20, then A33, A416, A595, 672. It grows pretty fast, but that A20 is immediately interesting.
Definitely. But wait, you started with A0 and A1 being 1. Is that consistent with the formula? And isn't there some debate about that at A0?
Ah, yes. You're right on both counts. The formula AN, bn plus 1 plus bn of 1, is given for n of 2. The A01 and A1 are given as starting values. And yes, there was a historical puzzle around a Yivero.
Okay, tell us about that. It sounds like the kind of thing you find digging through old papers.
It is. So Jacques Touchard, who did early work on this, has a 1953 paper in Scripta Mathematica. A table in there seems to imply a 01.
Okay.
But in an earlier 1934 paper in Comtes Rendis, an equation he gives, equation 3, actually implies A0A.
Huh. So his own work wasn't consistent.
Apparently not on this specific point. And William Orrick pointed out later, in 2020, that other formulas in the 1953 paper itself actually give incorrect results, unless you assume a 0 is really 0.
So why does the OEIS entry list a 01?
Well, this is where the OEIS acts partly as a historical record. The entry explicitly states it keeps the 01, specifically to agree with that table in Touchard's 1953 paper.
Even if it seems mathematically iffy, based on other evidence.
Exactly. It raises this interesting question, how do we handle these historical discrepancies?
Hmm.
OEIS chose to preserve the link to that specific publication, which is a valid curatorial choice, even if mathematically ADI might make more sense in the context of the formulas.
Yeah.
It shows the tension between history and consistency.
That was fascinating. It's like mathematical archaeology. Okay, so we have the theory, the history. Let's make it concrete. Can we walk through an example? Like, why is A2?
Sure. So A2 relates to permutations of n plus 1 plus 3, so permutations of 1, 2, 3. The identity is 1, 2, 3. The other reference permutation, one cycle, two cycle, would be, say, 132, fixing 1, swapping 2 and 3.
Okay.
Oric explains there are simply no permutations of 123 that are discordant with both 123 and 132. You can check them. 213 matches 132 at position 3. 231 matches 123 at position 1. 3 minus matches 123 at position 2. 321 matches 132 at position 2. None work, hence A20.
Okay, that makes sense. What about A3?
Right, so for A3, we look at permutations of 4, so 1233 for the identity is 1234. The other reference, 1 cycle, 3 cycle, could be the Harry 4, fixing 1, cycling 2, 3, 4, 2.
Okay.
And Oric lists the 3 permutations of 1234 that are discordant with both 1234 and 1342. They are 2413, 3421, and 4123. Only those 3.
Let's check one. Say 2413, does it match 1234? No. Does it match 1342? No. Okay, I see.
Exactly. And interestingly, to loop back to the A0 thing, Twitcher's 1953 paper also mentions a calculation for permutations discordant with 12345 and 13254.
Okay, that's M4.
Right. He uses an expression involving A4 plus the A0. The actual number of such permutations is 16. Now, we know A4 16.
So for the expression A4 plus A0 to equal 16, A0 must
be 0, which again supports the idea that maybe the A0 one from the table was, let's say, less consistent with his own formulas.
Wow, okay. It's like this little mystery woven into the sequence. These discordant permutations, they seem to have layers. Are there other ways mathematicians look at them, like generating functions or other formulas?
Oh, absolutely. There's often more than one way to describe a sequence. Vladeta Jovovich provided a generating function for A000270 back in 2007.
Right, the GF packs the whole sequence into one function.
Exactly. It's a powerful tool for analysis. And then Vaclav Kotasvek found a D-finite recurrence relation in 2014. It's a bit more complex. N3AN is 3N as N1 plus N3 as 2 plus N3.
Okay. That looks computationally useful, maybe. It allows you to calculate terms.
Very much so. D-finite recurrences are great for that. And Kosek also looked at the long-term behavior you asked about earlier. He found an asymptotic formula.
How the sequence behaves for really big N.
Precisely. It turns out AN is approximately N plus 1, XP2. So roughly N plus 1. Divide by E squared.
E squared again, like in derangements.
Exactly. That 1G factor often appears in problems related to permutations avoiding certain properties. Here, XCV2 suggests a strong connection to problems where you're avoiding, perhaps, 2 conditions, roughly speaking. It tells us the growth is very fast, factorial-like, but scaled down by this constant factor.
That's really neat. It's amazing how many different people contribute pieces to understanding just one sequence like this. It really highlights that the OEIS is like a living thing.
It absolutely is. It's a massive collaborative effort.
Yeah.
N.J. Sloan started it, but for A000270, we've seen key contributions from William Oric refining the definition, Lois P. Hines adding more terms, making more data available for people to analyze,
Right.
and then Jovovich with the generating function, Kochesovek with the recurrence and asymptotics, Olivier Danvy involved too. It's constantly being updated, corrected, expanded.
How do they keep it all straight? It's revisions and different perspectives?
It's a carefully curated database. There's an editorial process, new submissions, corrections, comments that get reviewed. It aims for mathematical accuracy and consistency, while also, as we saw with the Zero, sometimes preserving important historical context. It's a balance.
So wrapping this up, after this deep dive, you should have a pretty solid handle on discordant permutations. A000270. You know what they are? Permutations avoiding matches with the identity and that specific one-cycle-in-cycle pattern. You know, the link to Ménage numbers, which is pretty cool. You've heard about the historical detective work around a zero and seen how examples like A20 and A3 make it concrete. Plus, the different mathematical tools used to describe it, like the recurrence and the asymptotic formula.
Right. Hopefully it's a good shortcut to feeling informed about this particular sequence.
Definitely. So maybe a final thought to leave our listeners with. Something to chew on.
Well, thinking about those examples, we saw how to check if a permutation is discordant. But how would you actually go about finding or constructing all the discordant permutations for, say, N7 or N8? gets complicated fast.
Yeah, brute force seems tough.
Right. So how could you systematically generate them? Or, thinking about the OEIS updates, this sequence's definition was refined relatively recently. How might future research change our understanding, maybe find new connections, or even tweak the definitions of sequences we think we know well?
Good questions. It reminds you that math, even number sequences, is always evolving.
Exactly. There's always more to discover.